So it's my pleasure to introduce Luca Spolaor from University of California, San Diego, and he'll discuss isolated singularities for minimal surfaces today.
So thank you, Connor. Thank you, Feng, for the invitations and all the other organizers, since there are many for these talks. So I'm going to talk about isolated singularities for minimal surfaces. And I should say immediately at the beginning that I'm really not going to talk about isolated singularities. I'm going to talk about a subclass of them, which I will specify in a little bit. So the talk is divided essentially in three parts. I'm going to introduce very quickly minimal surfaces with optimal regularity and why they are interesting objects to study. And then I'm going to talk about two different types of results for isolated singularities of minimal surfaces, so convergence results, and I'm going to also talk about the generic behavior of singularities. Okay, so let me start with the basic definition. So as I said in this talk, I'm going to consider minimal hypersurfaces in some Riemannian manifold, smooth and closed. Okay, so you have your Riemannian manifold sigma with the metric G, it's closed, compact. And when I say minimal hypersurface, what I actually mean, for those of you who know what I'm talking about, I mean stationary integral varifolds, okay? So stationary integral varifolds are somehow geometric measure theoretic generalization of hypersurfaces that are sufficiently general to still be able to talk about the first variation, okay? So you just want to be able to consider the first variation of the area of the volume, okay? And you want to consider a large class where you maybe have compactness, where you can still talk about this operator, okay? And so when I say minimal hypersurface, this is what I mean. I mean stationary integral varifolds, and you can think this is just a generalization of smooth hypersurfaces, which still allow to be able to compute essentially the divergence. So the idea is that you have a tangent plane almost every point, okay? And I'm not going to study the most general class of stationary integral varifolds, so minimal hypersurface, but just the one which have a bound on the singular set. So I'm going to study the one for which the dimension of the singular set is at most n-7. So what is a singular point? Well, first of all, what is a regular point? A regular point is a point where your integral varifold is a multiple, a constant multiple of a smooth embedded minimal hypersurface, okay? So if at a point in a neighborhood, you are just a smooth embedded minimal hypersurface, that point is called regular. And the complement of this set is going to be called the singular set, okay? The regular set is open, the singular set is closed. And what I'm going to consider are only minimal hypersurfaces for which the singular set has at most dimension n-7, okay? So why am I considering this type of minimal hypersurface with this bound on the singular set? Well, the reason is this theorem. So whenever you have a compact smooth Riemannian manifold, there always exists a minimal hypersurface in the manifold with optimal regularity, okay? So this is somehow the most general class of minimal hypersurface that you can consider, okay? And which is always gonna exist in every compact smooth Riemannian manifold, okay? Of course, this theorem is very useful in differential geometry and topology. And what I'm gonna study in this talk are the properties of these minimal surfaces with optimal regularity, okay? So in proving this theorem, there are two different situations. I'm gonna mention this now. It will become apparent later why I wanna talk about this. And the two different situations are based on what happens to the topology of the manifold. So if the n-dimensional homology group of the manifold is non-trivial, then what you can do is you can minimize the volume in the homology class. So if the topology of the manifold allows you, what you want to do is you just want to look at minimizers of the area functional. Of course, in certain manifolds, this minimization procedure is just going to give you zero. It's just going to give you the trivial element of the homology group, right? But if you know that the homology group is non-empty, if you know that you have the correct topology, then you can just minimize. And when you minimize, of course, you know, in the class of smooth hypersurfaces, you don't have compactness. So to prove existence of minimizers, you need to enlarge the class. And then it's work of Federer, Fleming, De Giorgi, Almgren, Simons, and many other people that were able to prove that actually the minimizer in the homology group is going to be a minimal surface with optimal regularity, okay? I'm not going to talk about this, just to say you prove existence in a much larger class, but then at the end of the day, actually this minimizer is going to be a minimal surface with optimal regularity. If the topology doesn't allow you to minimize, which means that the homology group is, the n-homology group is actually going to be trivial, contains only the zero element, then there is another technique that one can use, and it's called min-max, in analogy with what you would do to find critical points of functions, right? And using this technique, you can still prove existence of minimal surface with optimal regularity. And this is due to the joint work of Almgren, to the combined work of Almgren and Pitts, who proved existence essentially. And then the work of Schoen and Simon, who proved the optimal regularity. Okay, there are other approaches nowadays to prove existence in the case where the homology group is trivial. And for example, the Allen-Kahn approach, which is a more PD approach, but I will not talk about that. But so what you should take from this slide is just the fact that these minimal surfaces with optimal regularity, so for which the singular set has at most dimension n-7, they appear essentially in every compact smooth Riemannian manifold. Okay? So these are the minimal surfaces that I want to study. And what do I mean by isolated singularities? Okay, so like basically in every problem in calculus of variation, in order to distinguish singularities, one singularity from another, what you do is you do a blow up. So the idea is I want to distinguish singularities based on what the infinitesimal behavior at the singularity is, right? So I want to look at tangent cones, essentially, right? At the tangent behavior there. And so what you do is you pick any point in the singular set. So suppose this is maybe your M. You want to pick any point in the singular set. And then what you do is you look at, ball of radius R there. You restrict M to that ball, and then you blow up the ball to scale 1. Okay. And then you want to see what happens to the limits of this blow up. Okay. So this is, if you started from a regular point, you would just get the tangent space to the point, right? That's what you would get. If you are looking at a more general situation, in general, at singular points, you cannot just conclude that you are going to have the limit and the limit is going to be a plane. However, there is a monotonicity formula. Again, this is a very common tool in many variational problems. And this allows you to take subsequential limits. So that means that after you're doing this rescaling, you can find subsequences that converges to 0, such that the minimal surface along the subsequence converges to a cone, okay? And the cone is going to be stationary. Of course, it's going to be in Rn+1, which here it's just identified with the tangent to, the tangent to the manifold at the point. And so at every singular point, up to subsequences, you are always going to converge to a stationary cone, okay? And then, okay, if you're studying stronger classes, so for example, if you're looking at area minimizing hypersurfaces, then the cone is also going to inherit the area minimality property. If you're looking at stable minimal hypersurfaces with certain bounds on the singular set, then you're also going to get that the limiting cones are all stable too. So essentially, if you have other properties on top of stationarity, they usually pass to the limit too, area minimality or stability. And of course, a first question that you can ask already at this point is this blow-up going to be unique? Because here, what I'm saying is that for every sequence, there is a subsequence along which you converge to a cone. So this cone might, of course, depend on the subsequence you're choosing. And so a very first question that you can ask, and it's usually the starting point to study regularity, is this subsequential limit actually the limit? Is it unique? I'm going to talk about that later on. But okay, the important thing now is that we want to use these limiting guys, these stationary cones, to distinguish different type of singularities, okay? And so I'm going to define isolated singularities as the subset of the singular set. So these are singular points for which every tangent cone at the point, so every limit of these blow-up subsequences, is a regular cone. So what does it mean to be a regular cone? A regular cone is a cone which has an isolated singularity, okay? So something that looks like this. And it has only one singularity at the origin. So basically, I'm calling singularities isolated if every tangent cone at the point only has isolated singularities, okay? So I'm calling a point an isolated singularity if the model has an isolated singularity there, okay? If the tangent model has an isolated singularity there. And another way to think about this is that every tangent cone at the point, if I intersect it with the sphere, so if I look at its cross-section with the sphere, this is going to be smooth embedded, okay? Because the only singularity is at the origin. So that means that if I intersect it with the sphere, what I see in the cross-section, what I see in the intersection is going to be smooth, okay? And in particular, being smooth, it also means that it's going to be connected. Because if I pick a cone, I intersect it with the sphere, the first variation is essentially only tangential. And so what happens is that if the cone is stationary, then the intersection with the sphere is stationary in the sphere, okay? And so it's a minimal hypersurface. And if I assume that it's smooth, now I have a minimal smooth hypersurface in the sphere. And by the maximum principle, it cannot have two disjoint connected components, otherwise they would touch and then they would coincide. And so I can also assume that the cross section of this cone is connected. And so really the picture for a cone, for a regular cone is something that looks like this. So something that splits the space into two parts, okay? And then I'm also gonna consider another subclass of these isolated singularities, which are the class of isolated singularities which are area minimizing. And by these, I simply mean that not only the cones at every tangent cone at the point is regular, but it's also area minimizing, okay? So it's a little bit of a smaller class with respect to the class stationary cones. Okay, and as I said at the beginning of the talk, I should mention that every point in this class, every point in this class S0 is indeed isolated in the sense that there cannot be a sequence of singularities converging to it, okay? Otherwise, what you do is you blow up along the sequence of singularities and you see that the limiting cone should have a line of singularity. That's basic stratification, okay? And then that would violate the definition of S0 as the point at which every cone is actually a regular cone, okay? But it's not true the other way around. At least, you know, I don't know of any example, but it should not be true. There should be an example of this, of which, you know, a point which is isolated, but so it's a singularity which is isolated, but at which, if you do blow-ups, you converge to a cone which actually has a line of singularity, for example. So, you know, in a picture, my picture is not going to be very nice, but what I'm thinking is your cone looks like this, your blow-up looks like this, but the actual minimal surface close to that somehow looks like this. So it's smooth and it's singular only at this point, even though the blow-up at the point has a full line of singularities, okay? So you could have examples of isolated singularities for which at least one blow-up is not actually regular, okay? And so that's why when I say that I'm talking about isolated singularities, I'm cheating a little bit, because the class of isolated singularities should be a little bit, could be larger than the one I'm actually considering, okay? So once again, for me, isolated singularities are the one for which every cone at the point, every tangent cone at the point has an isolated singularity, okay? Okay, so these are the type of singularities that I want to study. Why are they interesting? Well, they are interesting because they exist. Okay, so there are examples of singularities of this type. And the basic example is the class of Simon's cones. Okay, sometimes they're also called quadratic cones. So these are cones denoted by CPQ usually in the literature. And so P plus Q has to be at least 6. And then they are defined through this balancing condition. So Q times the absolute value of X equal to P times the absolute value of Y. They are all area minimizing. This is due to Bombieri, De Giorgi, and Giusti for P equal to Q equal to 3. And then, for example, Simon's for all the other P and Qs, except for one of them, 2 actually, which is the case P equal to 1 and Q equal to 5. And so, of course, also P equal to 5 and Q equal to 1. This one guy here, is not area minimizing, but it is still area minimizing on one side, which means that if you do perturbations to one side, they are going to increase the volume. But if you do perturbations on the other side, they might not increase the volume. Okay? And all these cones are regular, and you can see this because if you intersect them, well, you can see it by the definition, but in particular, if you intersect them with the sphere, with the n-dimensional sphere, the cross-section is a product of spheres. So it's SP times SQ, okay? So it's smooth embedded minimal hypersurface in Sn. Minimal by, you have to rescale the radius, of course, to put them in an Sn. Okay, so this type of singularities that I'm interested in. And of course, this is just an example. There are many other examples of isolated singularities, okay? Except in dimension 6, so n equal to, 7, except in dimension n equal to 7, then it's not known if there are other examples of area minimizing, at least, isolated cones with isolated singularities, except for the CPQ cones. Okay? Okay, so now let's start talking about results, some results about this type of singularities. So the first result that I want to mention is a uniqueness of blow-up type result. Okay, so as I said, when you do rescaling at the point and you look at the possible tangent cones at the point, they might depend on the subsequence you're looking at because you're using some kind of compactness there. And so the first interesting result is the following, which says that if you pick any isolated singularity, so any point in this S0, then the blow up at the point is actually unique. And moreover, the minimal surface that you're looking at in a neighborhood looks like a graph, is a graph of a C1 log function over the cone. So the picture that you can have in mind is that you have your cone, okay? And you cannot have any other cone tangent to the minimal surface at the point. And indeed, the minimal surface itself looks like a graph, okay? And the modulus of continuity of the gradient is going to be logarithmic. So if you want to think about this in another way, if you know what the flat norm is, what I'm saying is that the distance in flat norm of the minimal surface to the cone in the ball, radius 1, is decaying as a constant time absolute value log r to some power minus epsilon. Okay, so you are converging, the sequence of blow up is converging to the cone, okay, and the modulus of continuity, or if you want the rate of convergence, is going to be logarithmic, okay, a priori. So it's not necessarily a power of the radius, it might just be logarithmic. So one way of thinking about this result is precisely that, you know, the sequence of blow up, which is a sequence of minimal surfaces, is converging to the cone at a logarithmic rate, okay? Now, of course, another question you can ask, okay, and I should say this result is due to Leon Simons in '83, and we gave a slightly different proof, but the basic idea is due to Leon Simons. So this is really a result about the convergence of a sequence of minimal surfaces to a limiting I, except that your sequence is obtained in a very specific way. It's obtained by rescaling a fixed minimal surface at a singular point, okay? Of course, you can ask a more general question. And so you can ask, okay, suppose that I have any sequence of minimal surfaces, not necessarily obtained through rescaling of a starting one at a singularity, which is converging to a cone with an isolated singularity. Can I still say something about this convergence? Can I, for example, say something of this type? So some rate of convergence or something like that. And so, or more importantly, can I say something about the behavior of the, you know, the singular or regular behavior of the sequence that is converging to this limiting cone? And this is a question that we asked with Nicolas Hedelen, assistant professor at Notre Dame. And the theorem that we managed to prove is the following. So suppose that you have a sequence of minimal hypersurfaces, which is converging weakly, okay, to some cone of type PQ. So some of the quadratic cones that I introduced above, whose intersection with the sphere is a product of sphere itself. And assume that this CPQ is actually area minimizing, okay? So that if you do variations on both sides, you increase the volume. And so every cone essentially, except for the case 1 or 5. Then, you know, for I sufficiently large, the sequence that is converging has to be either smooth, or it can have at most one isolated singularity of the same type of the cone. So let me try to explain this. So what I'm saying is essentially the following. So you have your limiting cone, and your limiting cone is of type CPQ. It's a quadratic cone, so it's a very specific type of cone. It's not any area minimizing cone with isolated singularity. It has a very specific form. And then you have a sequence which is converging to it, or sequence of minimal surfaces which is converging to it. Then this sequence can only do two things. So either it has an isolated singularity somewhere, and this isolated singularity after blow up looks exactly the same as the cone. Okay, so if I do blow up at that singularity, I see exactly a cone of type PQ. Okay, or the only other possible behavior that they can have, that such a sequence converging can have, is to be completely smooth. So the other possibility is that the sequence converging there is just smooth. Okay. So whenever you have a sequence of minimal hypersurfaces converging to a cone of type PQ, okay, only two things can happen. Either the sequence has exactly the same type of singularity as the limiting cone, and only one of them, or it's completely smooth, so it has no singularities at all. Okay. And this is interesting because a priori several worse things could happen. For example, you could have different type of singularities coming together along the sequence and converging to the limiting singularity, right? One possible picture that this theorem rules out, for example, is your sequence could look like this, maybe, right? So you have two singularities, and then in the limit they come together in the limiting singularity of the cone. Well, this is not going to happen. This is something that our theorem rules out. Okay. So it tells you that in this type of convergence, this type of singular convergence can only have two behaviors, either completely smooth convergence or with the same type of singularity. Okay. Of course, then this can be generalized to sequence of minimal surfaces converging to a limiting minimal surface, which has only singularities of type PQ. Okay, and then the sequence can only converge smoothly or with singularities of type PQ. And I should also say that I restrict here to cones of type PQ. Actually, it holds for a slightly more general class of cones, but not for every cone. Okay, or at least we don't know if it holds for every cone. I don't think it's true, but I don't have a counterexample to that. Okay, so let me say two words about why this result is optimal. Okay, so of course you can have convergence with the same type of singularity. For example, a blow-up sequence is going to converge with the same type of singularity. Okay. So what is different between this theorem and the previous one is that in principle, you could also have this smooth convergence, okay? Convergence from smooth minimal hypersurfaces converging to this limiting cone, which has an isolated singularity, okay? So how can you construct such an example? Well, this is a very famous construction by Hart and Simon. So what they did is the following. They proved that for every cone which is area minimizing and regular, so which has only one isolated singularity, then there are unique smooth area minimizing hypersurfaces as plus minus contained in E plus minus. So the picture is this. You have your cone, okay, which you can think of as the boundary of two connected components. So the cone splits the space into two connected components, splits Rn plus 1 into two connected components, okay? And you can think about the plus and minus, say, okay? And then what Hart and Simon proved is that in each one of them, there is a unique minimal, actually area minimizing hypersurface, which at infinity is asymptotic to the cone, okay? Which is at distance 1 from 0, okay? And which is completely smooth, okay? So both in E minus and in E plus, there are such surfaces and they are unique, okay? And they are completely smooth. Not only they are smooth, they are also what's called a radial graph, which means that if you pick any radius from the origin, that's gonna intersect the minimal surface, the right minimal surface, only at one point, okay? So given this property, what you can do is you can consider dilations of this S plus and S minus. So this guy here, I'm gonna call it S minus, this guy S plus, okay? You can consider dilations of them. And once you consider dilations, they are not gonna overlap because they are radial graphs, okay? Because of this property that any radii from the origin intersects each one of them only at one point. So you can dilate them. And the union of all these dilations is gonna cover the whole space. That's why it's called the foliation, okay? So what you do is you use this as plus minus to construct a family of minimal hypersurfaces as lambda. And this family is gonna be, as I said, dilations of S plus and dilation of S minus, okay? And the zero slice is just gonna be the cone itself. And this is just a covering of the whole space, disjoint. So with this, now you see why the previous result is optimal, because now if you pick this family as lambda and you let lambda go to 0, okay, what happens to this family is that it's converging to the cone, okay? So if you let lambda go to 0, you are sending this surface back to the cone, okay? And the convergence is happening smoothly because each one of these red guy is a dilation of a single smooth guy, okay? So all of them are just smooth, okay? So this tells you that the previous result is optimal in the sense that you can definitely have smooth convergence to a singular object, okay? By the way, this is also the existence of this foliation is also how you prove that those cones are area minimizing. So it's almost an if and only in the sense that if you have an area minimizing cone with isolated singularity, you have the foliation. And essentially all the examples I know where you can prove that the cone is area minimizing is because you can construct a foliation. So it's kind of an if and not if. Okay, so let me mention briefly how you try to prove this type of results. So both the uniqueness of blow-up result and both this type of convergence of minimal surfaces, of sequence of minimal surfaces to a cone with isolated singularity. So the starting proof, since this is a PDE seminar, maybe I want to go directly to PDE. And the idea is that you want to reduce yourself to a graphical situation so that you can actually talk about PDEs. And the idea is the following, and here is basically where the fact that we are studying cones with isolated singularities, so regular cones, is very important. Because what you can do is you can remove a small neighborhood of the singularity, okay? And if you do that outside, in any annulus outside, you are gonna be just graphical. Oops, this is not supposed to happen. Your minimal surface is gonna actually be graphical and actually a regular smooth graph up to here, okay? So this is a consequence of Allard epsilon regularity theorem. If you don't know Allard epsilon regularity theorem, it just tells you the fact that if you are very close to a plane, then you have to be smooth. If your minimal surface is very close to a plane in some suitable norm, then you have to be smooth, okay? And since your cone is singular only at the origin, anywhere away from the singularity, so away from the origin, your cone looks like a plane, essentially, okay? Or at least it's smooth, so infinitesimally looks like a plane. And so you can just prove that the minimal surface, which is very close to the cone, away from the singularity, is just gonna be smooth there, okay? So out here, I can just write my minimal surface as a graph of some function u. Okay, normal graph, so normal over the cone. And so this is what this equality is telling you, that away from, I cannot just write the whole minimal surface as a graph, not yet, because I don't know what happens close to the singularity. But if I stay sufficiently far from the singularity, then I can do that. I can just write it as a graph. Okay. And I choose to write it as a graph, which is almost one homogeneous. So what I care about is how much this graph is not one homogeneous, because the idea is that now I want to prove that this graph is going to decay faster than one homogeneous, right? Faster than linear, so that then the blow up is going to be unique, right? Because decay is lower than one homogeneous would still allow you to change the cone. Decay that is faster than one homogeneous fixes the cone. You cannot escape from it. So the idea to prove regularity is essentially, okay, first I write myself as a graph away from the singularity, and then I try to prove that this graph is decaying. Okay? It's decaying faster than linear in a suitable norm. So here I'm hiding a lot of stuff. You cannot completely forget about the geometric problem, because a lot of crazy things could happen inside of this ball, and you have to rule out that those crazy things happen. But for the sake of this talk, let me just say how you actually try to prove decay of the graphical part. And the idea is simple in some sense. The idea is to look at the linearized problem, as you would do in basically every type of elliptic problem. And so what you do is the following. You look at the linear part of the minimal surface equation for graphs over the cone. So you have this graph over the cone. You can look at its minimal surface equation. You know the graph is going to solve the minimal surface equation because I'm assuming it's a minimal surface, right? And then I can look at the linear part of it, which is called the Jacobi operator. And I can write the Jacobi operator in polar coordinates. So there is a radial part, which is the same radial part that you would have with the Laplacian. And then there is a tangential part, okay, which happens on the cross section. This is completely fine, well defined, because the cross section of my cone is just smooth. So this thing is just, a very well defined operator, elliptic operator. And what I want to do is I want to write every solution of the Jacobi operator, so of the linear part of the minimal surface equation in an eigenfunction expansion. Okay, so what I can do is I can look at the eigenfunctions Vj with corresponding eigenvalues lambda j of the tangential part of the operator. Okay, and then what I do is I take the harmonic extension. These are not harmonic; they are, of course, the one adapted to this operator of the corresponding solutions. Okay, and so what I can do is I can write any solution of the Jacobi operator in this form, where the Vj's are the eigenvalues of this operator, and the lambda j's are the Vj's are the eigenfunctions of this operator, and the lambda j's are the corresponding eigenvalues. And so the homogeneities, gamma j plus and gamma j minus, are obtained simply by this form. Okay, so this is just basic Fourier analysis, right? I'm just writing any solution in Fourier expansion. Okay. And now what do you want to do? I said, right, I mean, if you look at how I wrote my graph, what I need to guarantee is that my u decays at least like as some power of r, or at least you know, faster than zero homogeneous. U must be faster than zero homogeneous. Faster than zero homogeneous because I already put this absolute value of x here. Okay? And so what I need to do in this expansion, I need to kill every mode, right? I need to be able to kill every mode that is you know, for which gamma j is going slower than zero homogeneous. So for which gamma j is less than or equal than zero. Okay. So the idea is, in order to prove decay, what I want to do is I want to say that if gamma j plus minus is less than or equal than zero, then the projection on the corresponding modes is just going to be zero. Okay. If you can do that, if you can prove that for the graph, right, then the graph having this expansion essentially up to the fact that I'm looking at the linearized operator and not the nonlinear case, right, it's going to decay in the right way. Okay. So in order to prove this fact, there are two different strategies depending on what type of result you want to prove. So if you're looking at blow-up sequences, okay, as I said at the beginning, the good thing about blow-up sequences is that they are obtained by rescaling the same guy. And you are rescaling the same guy at a singular point, okay? So if you're looking at a blow-up sequence, what you know is that 0 is a singularity for every element of the sequence, okay? Because what you're doing is you're picking a singularity, translating back to 0 and dilating. And that's how you are constructing your sequence of minimal surfaces, right? So 0 is always going to be there. It's always going to be a singularity. So if you know this, a consequence of this is that your graph from 0 is going to grow at least one homogeneously. Okay, so this is a complicated proof. It's an estimate by Hart and Simon, and that allows you to prove that, you know, whenever you know that 0 is a singularity, then all the modes which are strictly less than 0 are gone. There cannot be anything which is less than, for which that cannot be the projection on the modes which are less, for whose homogeneity is strictly less than 0 are just gone. They cannot be there. Okay? And that is a consequence of the fact that 0 is a singularity at the point for all the elements of the sequence. Okay? So once you know this, that means that the only ones that you are left to kill are precisely the ones which are equal to 0, for which gamma j is equal to 0. Okay? If you go back and look at this expression, then you realize that gamma j equal to 0 corresponds to lambda j equal to 0. Okay? So the one that you need to kill are precisely the ones that are in the kernel of the tangential part of the operator, okay, of the Jacobi operator. So the ones that you need to kill are the ones that corresponds to solutions of the tangential part of the Jacobi operator. Okay. And so your expansion is reduced to this form, right? So in everything that was below gamma j plus in the kernel is gone, and the only things that are left are the one in the kernel. Okay? In the kernel of the tangential part of the operator. In the other case, instead, in the case where you just have any sequence converging to a cone of type CPQ, okay, now you don't have the strong property that every element of the sequence has a singularity, right? And in fact, the theorem states that you could have the situation where you don't have any singularity at all, right? And so you lose this property. You lose the growth as one homogeneous growth. So you cannot just kill everything which is below, strictly below 0. Nevertheless, what you can do is you can use the foliation. So I told you, if you have a cone with an isolated singularity, then Hart and Simon constructed these minimal surfaces. Okay. And you can use them, these minimal surfaces as lambda, as barriers, essentially. Okay. Just to say that, you know, whatever minimal surface, graphical minimal surface you have, it has to be trapped between two leaves of the foliation. Okay? And being trapped between two leaves of the foliation essentially implies a certain growth condition. It means that you cannot grow any faster than the foliation itself. Okay? As you go towards 0, if you want, you cannot blow up faster than how the foliation is blowing up towards 0. Okay? Essentially just by the maximum principle. And so using the foliation and the maximum principle, what you can do is you can kill a lot of modes, but not all the ones that are strictly less than 0, because the foliation itself is not one homogeneous. It's actually blowing up as you go towards 0. And so what you can do is you can reduce your expansion to this expansion here, which says that, okay, everything that is below the foliation I can kill by the maximum principle, but then I'm still left with the foliation element, okay, which is essentially just the positive eigenfunction. And then I have translations, and then I have rotations, okay? And then I have things which are decaying faster than one homogeneous, okay? So faster than 0 homogeneous. So what I'm saying here is the following. If you have the information that 0 is a singular point for all the elements of the sequence, then you can kill every eigenfunction for, you can kill the projection on every eigenfunction for which gamma j is strictly less than 0. If you don't have that, you can only kill the one which are below the foliation, okay, by using the maximum principle. But you have a stronger property here that I'm restricting myself to cones of the form CPQ. For cones of the form CPQ, this operator here is very explicit. In particular, the absolute value of the second fundamental form is just a constant. So you can write the Fourier expansion explicitly, okay? And you can just write it in this form. So you know exactly what are the terms that you are left with. While here, I don't know what is in the kernel because I'm assuming just that the cone is area minimizing and I don't have an explicit expression for it. It's not just a CPQ. Okay? So the advantage here is to know exactly the structure of the cone, but on the other hand, I don't know about the singularity. While on this case here, I know exactly the singular behavior of the sequence, but I don't know the specific structure of the operator because I'm not assuming any structure on the cone. So in this case, I want to kill these guys, and in this case, I want to kill all these guys. How do you do that? Well, so to kill the elements in the kernel, this is the fantastic idea of Leon Simon. What you can do is you can use the so-called Loyalist inequality that basically allows you to write your area functional as an analytic function over the kernel, okay? And then once you have an analytic function over the kernel, you can use this Loyalist inequality that allows you to prove a logarithmic type decay, okay? Even without knowing anything about the structure of the kernel itself. And like, you don't know if every element in the kernel comes from some rigid motion of the space, like a rotation. Even if you don't know that, this Loyalist inequality still allows you to prove decay. But the drawback is that the decay is going to be logarithmic. Okay, I don't want to enter into this, but the point is that even though you don't know anything about the structure of this kernel, just because it's finite dimensional, because you're looking at an elliptic operator in the sphere, right, on a compact manifold, just this fact allows you to prove decay. Okay. On the other hand, instead, in the second case, what you can do is, here it's very clear what you want to kill. You want to kill foliation, you want to kill translation, and you want to kill rotation. These are all rigid motion, not rigid, but these are all, they all come from motions in the space, from clear, operations that you can do in Rn+1. And so the way you kill them is just by reparametrizing your graph on the correct translation, on the correct rotation, and on the correct foliation. So what you do is you translate the cone, maybe you rotate it a little bit, and then you move up in the foliation, wherever you need to go. And if you parameterize yourself over this correct choice, then you can just kill all these modes. And so you are left only with Dyer-Holder terms, okay? So in the second case, it's just a matter of reparametrizing yourself well on the correct object. In the first case, instead, you have to do something smarter, which is using this Loyalist inequality. Okay? Because you don't know that just some movement of the space is going to be enough to kill everything which is in the kernel. Of course, the drawback of the second case is that if you do reparameterize yourself over the foliation is smooth, and so you are going to end up being smooth yourself. And so that's where the smooth convergence can come from. Okay, so these are the basic ideas for these two results. So the idea is you try to look at the linearized operator, you try to look at the modes which appear there, you try to kill everything which is not decaying at least faster than one homogeneous, and then you have to use different tools, either the presence of singularities or the foliation to kill them, and then some rigid motions of the space or the Loyalist inequality to kill what's left. Okay. Now let me move to the second part of the talk. Is there any question? Okay, so if there is no question, then I'm gonna go on. And so in the second part of the talk, I guess I have another 10 minutes, maybe a little bit more, is generic regularity. So I promised at the beginning that I would talk about convergence type result and then about some generic regularity type results. So what do I mean by generic regularity? So suppose you have your Riemannian manifold, sigma, and denote by M metric 2 alpha the collection of all the C2 alpha metrics for the manifold. Okay. So Smail in '93 proved the following result. It proved that if you have an 8-dimensional compact smooth manifold, for which the homology group is non-trivial, remember this just means that you can consider area minimizing or homology minimizing objects, right? So you don't need to just look at critical points, but you can literally look at minimizer of the area, okay, in the homology class. Then he proved that if you can minimize, essentially, this is just a topological condition, right? Then there is an open and dense set of metrics that you can put on the manifold, such that for each such metric, so for each metric in this open and dense set, there exists a smooth embedded minimal hypersurface, okay? So the difficult part of this statement is the denseness. The open part is not very hard to prove. The difficult part is denseness, so the fact that this set is dense. And the idea for dense is like you start from one which has singularities, and then you try to construct another one which lives nearby, so another metric which lives very close to the starting metric, right? For which the new minimal surface for the new metric does not have any singularity, okay? So you can think about this result as perturbing away singularities. You try to perturb your original minimal surface, which might have singularities, into a nearby one, which does not have any singularity at all, okay? There are some similar results in the literature, and they are all in the minimizing context. So when you are considering minimizers and not just minimal surfaces, but minimizing surfaces, okay? And for example, White and Moore proved that you can remove branch points of minimizing area minimizing surfaces in high codimension. And White proved generic regularity for minimizing surfaces mod 2. But these are very specific of the type of singularities that you are considering. And they are both in the case of minimizers. So of course, you know, the question now is what happens if I remove this condition, right? Because I told you at the beginning, this theorem of Almgren-Pitts and then Schoen-Simon allow you to prove existence of minimal surfaces with optimal regularity in every manifold, right? But they can have singular set, right? And Smail tells you that if these are minimizing, then you can perturb away the singularity. What happens if they are not minimizing? What happens if I remove this condition? So together with Otis Chodos in Stanford and Evgeny Lyokumovich in Toronto, we proved the following two results. So we proved that if you have a compact smooth 8-dimensional manifold, then there is an open dense set of metrics with positive Ricci, okay? Such that for each metric in this set, in this dense open dense set, there exists a smooth embedded minimal hypersurface. So this is the analogous of Smail, where instead of the topological condition that was there before, that allowed me to minimize, this time I might not be able to minimize, but what I'm assuming is that I'm looking only at metrics with positive Ricci tensor, okay? More generally, and perhaps more interesting, is this result. And this says that whenever you have a compact smooth 8 manifold, then there is a dense set. Here I cannot prove openness, only denseness. There is a dense set of metrics in C2 alpha, such that for every metric in this dense set, there exists a smooth embedded minimal hypersurface, except at most at one point, okay? So it's not as good as Smail, and it's not as good as the positive Ricci case. In principle, what we can prove is that in every manifold, in every 8 manifold, you cannot just perturb away every singularity, but you can perturb away everything except of most one singularity, okay? So you can prove that in every 8 manifold, for a dense set of metrics, there exists a minimal hypersurface which has at most one singularity. But it could, we don't know, this is actually an interesting question. We don't know if the result is optimal. Is that singularity there or not? We don't know. But I'm gonna explain you why we cannot, I mean, we don't know, and why the best we can prove is at the moment is this, at most a single, at most one singularity. So, okay, these theorems, they are both 8-dimensional theorems in the sense that we're working in a dimensional manifold. Actually, they are valid in higher dimension, but if you want to state them in higher dimension, you cannot just perturb away the singular set. You can only perturb away isolated singularities. Okay, so if you go to higher dimension, then you can have a bunch of different type of singularities, not just the one which are isolated. You can have lines of singularities or whatever, right? And what we can prove is that essentially in every n+1 dimensional manifold, there is a dense set of metrics for which there is a minimal hypersurface with optimal regularity, which has at most one isolated singularity. Okay, but we cannot say anything about the rest of the singular set. We can only say something about the isolated singularity. Okay, so how does one try to prove a result like this? So the basic idea goes back to Hart-Simon again. So all these theorems are interconnected with each other. And the Smale proof goes this way. So the idea is that if I can, we saw before that if you have a cone with isolated singularity, then you have this unique foliation. So you have this smooth guy up and this smooth guy down, which are unique if you fix their distance from the origin, okay? And then they construct a whole foliation. So the idea is that if I have a minimal surface, or an area minimizing surface with some isolated singularities, and I know that I converge to this guy, to this limiting guy from one side. Okay, so I have a sequence of minimal surfaces, say MJ, which is converging to a limiting one, but from one side. Okay, then if you rescale, if you do a blow up in a correct way, you can reduce yourself to this situation, to the situation of looking at a cone and the sequence converging from one side to the cone. And then again, essentially by the maximum principle, you can see that convergence from one side to the cone means that you have to be an element of the foliation. But the foliation is smooth. So the idea is that if I have a minimal surface with isolated singularity, and all the singularities are somehow area minimizing, okay, and I'm converging from one side, then the convergence has to be smooth. Because in the limit, or infinitesimally, you have to be a leaf of the foliation, okay? So the idea is that around every area minimizing singularity, you have a foliation, right? And then you can just use the maximum principle to say that you have to end up in one of the elements of the foliation. And so Smale idea is just, okay, since this is true for area minimizing cones, okay, and for sequences of area minimizing hypersurfaces, then his idea is I just need to cook up a metric, a change in the metric that will force minimizers to move to one side with respect to the original minimizer. Okay, so I start from one minimizer, I want to perturb it. I want to perturb the metric so that for the new metrics, the new minimizers are going to be smooth. So I just need to perturb the metric in such a way that the minimizers for the new metric are going to go to one side of the original one. And then as they converge back, they're going to end up infinitesimally looking like the foliation, and so being just smooth. Okay, so that's his idea. The problem with this idea is that you need to know that the tangent cones at every point of your minima surface are area minimizing, because what he's using is heavily defoliation. Now, whenever you have a foliation, as I said before, having a foliation by minimal hypersurfaces around the cone implies that the cone is area minimizing. So if you had a cone which was just stationary or even stable, okay, but not area minimizing, then there cannot be a foliation for that cone. Otherwise, that cone would be area minimizing, okay? And the problem is that when you try to construct things using min-max, and so in the case where you don't have this topological restriction, you cannot guarantee that the tangent cone at every point for your minimal hypersurface is going to be actually area minimizing. A priori, it's just going to be stationary, maybe stable, but no more than that, okay? So you might not have defoliation, okay? So that might be a problem in trying to perturb away singularities. So, so our idea with, let me skip to that since I have 2 minutes left. Our idea with Otis and Yevgeny was, okay, when you do min-max, you might end up having a minimal hypersurface, which at every singular point does not have area minimizing tangent cone. But in how many points is this going to happen? How many points, how many singular points for your minimal hypersurface are actually not going to be area minimizing, okay? And so our idea is, okay, maybe if you do min-max in a smart way, you can actually control the number of singularities, of isolated singularities, which are not area minimizing. Okay, and so this is precisely what we do. So what we do is we prove that given any closed Riemannian manifold of dimension n+1, there is a minimal hypersurface with optimal regularity, which realizes the width. This just means that if you are doing min-max in a proper way, it's not so important. The important thing is that you do end up with a minimal hypersurface with optimal regularity, for which you have a control on the number of singularities, which are not of isolated singularities, which are not area minimizing. Okay, so what we prove is that this minimal surface is such that the number of isolated singularities which are not area minimizing plus the index of the regular part is less than or equal to 1. Index of the regular part just means the number of directions which decreases the area, moving just the regular part. Okay, so without moving the singularity. And so you see, the consequence of this theorem is what? Is that essentially the idea now is, okay, I should be able to apply the same strategy here, so to use the foliation to perturb away singularities. But if I want to do this, I can only do this at singularities which are area minimizing. Okay, that's the drawback of this. And what we prove here is that, well, okay, you can actually do it at every point except for at most one, because every point is going to be actually area minimizing except for one of them. Okay, and that's why the result that we can prove is just up to one singularity. Every other singularity you can just perturb it away. Okay, so it is, as I said at the beginning, it is an open question if you can improve the result to just saying that there is actually no singularity at all. Okay, and the open questions in that directions would be, first of all, one would need to prove or disprove the fact that there is a stable regular cone which is not area minimizing on either side. Okay, so this is an open question. We don't know if there is a stable cone which is not area minimizing to at least one side. Okay, it is known that there is one which is not area minimizing. I told you before, it's the cone over S1 cross S5. This guy is not area minimizing, but it is area minimizing to one side, and that's enough. Okay, you would need to prove that there is actually no such cone, or that there is such a cone, and then try to construct an example. And then even if such a cone exists, it's still a question if the above bound is optimal. But the conjecture is yes. So we believe that if there is a cone which is stable but not area minimizing, then there should be an example. And indeed, this happens in dimension 1. So in dimension 1, there is this famous example of the figure 8 on the jellyfish. So you take this manifold M, and then you look at this curve C. This curve C is a geodesic. Okay, so it's in particular a critical point of the area of the length, right? And you see that if you do blow up at this point, what you're going to see is the union of two lines crossing at the origin. Okay, and this cone is stable, but it's not length minimizing, area minimizing, right? You can just shorten the path by joining the two lines like this. Okay, so in this case, for example, and if of course this is a singular point that you cannot perturb away. So in this case, the bound is supposed to be optimal. So I think this is an interesting open question that we cannot answer though. Another interesting open questions that we cannot answer is whether or not these minimal hypersurfaces that we get here are actually min-max hypersurfaces. Because in Smale can prove that up to, generically, there is actually a representative of the homology group, which is smooth. We cannot prove that these minimal hypersurfaces that we construct generically, which are either smooth or with at most one singularity, actually come from a min-max procedure. So maybe if you do min-max in an even smarter way, you can just perturb away every possible singularity. We don't know about that. Okay, I think I'm out of time, so I'll stop here. And thank you for your attention.
Okay, thank you, Luca, for this very nice talk today. Do we have any questions for Luca? Well, I've got a question. So, well, my first one is there like a version of Hart-Simon for minimal cones which are just one-sided?
Yes.
Okay, so you get the foliation from that side.
You get the foliation on that side, yes.
Okay.
It's not
so
that actually Ard and Simon themselves essentially prove it, in the sense that the idea is, the idea is you move to one side. So, the cone splits the space into two parts, right?
Yes.
And you move the boundary a little bit to one side, okay? And then the important thing is that when you minimize now with respect to this new boundary, you don't cross on the other side. And so the fact that you are minimizing to one side, if you're doing this procedure in the correct side, implies that you cannot just cross on the other side, essentially by cut and paste. Because if you were crossing, then you can cut, right, and replace with the cone, and then you would have an area minimizing hypersurface, which has too big of a singular set. So yeah, so essentially Ard and Simon themselves already prove this. And actually this is what we use, because in our proof of generic regularity, we can only prove that this hypersurface is minimizing to one side, except at a point. So yeah.
And you make the perturbations to make them lie on that side.
Yes, yes.
I see. Thanks.
Yeah. Thank you.
I also have a question.
Ciao, Francesco.
Ciao, Luca. So it's about the first result you have shown, the one about the somehow generalizing Simon's result rather than looking at blow-ups as sequences of manifolds, right? So I wanted to ask you if, I mean, at least the way you describe the proof, right? It's based on an analysis of the Jacobi operator of the cone. And I was wondering if then the extension to surfaces, say, with bounded mean curvature could be somehow, I wouldn't say easy, but doable, let's say.
Well,
or if there are things that I'm completely ignoring at this point. And
no, that's a good question. So the issue is, depends what you want to prove. So the issue is, if you just want to do exactly what I said, you need to use the foliation. So because the critical tool in the argument is to use the fact that, as you are converging to the cone, you are graphical away from the singularity. And then you want to use the leaves of the foliation as barriers. And the leaves of the foliation, the foliation, of course, is generated by one of these Jacobi fields, right? By one of these, by one of these modes, right? Right here. And it's actually generated by the positive one. So the one that is just, constant positive. And so that one is exploding as you go to zero. So it's not decaying, of course. It's going as, as you see as a function of R, it's blowing up, okay? And the point of the foliation is that if you use the foliation as barrier, you can say that the worst any sequence converging is doing towards the origin is blowing up as fast as the foliation. It cannot blow up any faster than that, okay? But in doing so, you see, you are using something about the equation. You are using the fact that you have solutions of the minimal surface equation that you're using as barriers. Okay? So it's not so easy to, I don't see immediately how to generalize these two different operators, because now you're changing my operator, right?
Well, okay, so let me say this then. I think it would be interesting to have the same theorem rather than, so forget about the CMC MIs. So just with this kind of slightly, it seems slightly, but I don't think it's so slightly. So I think it's interesting to have the mean curvature of your surface is not to be zero, but to go to zero. So say that you're, to start with, they're going to zero uniform. The mean curvature is going to zero uniformly. It's zero.
Then it's true. Then it's true by compactness. We proved that too.
Can you do that with the mean curvature that goes to zero in L2?
No, I think we do it with the mean curvature that goes to zero in LP for P larger than N. So the usual, usual threshold for, for regularity.
For the regular. I think that the case of the mean curvature that goes to zero in L2 may be very interesting because it's somehow the natural bounds you have for the mean curvature flow. So the dissipation of the mean curvature flow would be the integral of h squared, and as time goes to infinity, that should go to zero, right? So I don't know. Somehow I think that if you do this kind of regularity theorem so this mean curvature small in L2, you may be able, for example, to show what the mean curvature flow does when you fix the boundary data and you try to converge to the Simon's cone, for example.
Yeah, no, you're right. That's a very good question. I don't have a good answer for that. I think it might be quite tough to generalize to generalize.
Okay.
But I might be wrong. I have not thought about this. Thank you. Yeah,
okay, thanks.
Hey, Luca. Hey, Luca.
Hey, how are you?
Good, how are you? So I have a question about your theorem with Max, actually, the one about C1 log graph.
Mm-hmm.
So in this type of result, is there any way to get a lower bound to show like the log is the optimal regularity you can get?
That's a good question. I know only of two situations where it's the log has been shown to be optimal. One you certainly know, it's the one in the obstacle problem, the one of Alessio and Joachim on the obstacle problem. And then there is a theorem by Adams. I mean, there is a paper by Adams and Simon where they prove for a very specific cone and in codimension 2 though, not in codimension 1, they prove that the convergence has to be logarithmic, essentially by proving that there is something in the kernel which cannot be killed by any rigid motion of the space. So they prove that there is a cone which is non-integrable. Right? And then they show that essentially the second variation is 0, but the third variation along that direction is not 0. And so they use the fact that the third variation not being 0 in that direction is what gives you the decay. But because it's third and not second, then you decay as a log instead of as a power. Those are the only two examples that I know. I might have skipped some. I mean, there might be others. I don't know.
Yeah. So it's not known if this is optimal in general. Like there's no way just by using say Loyalist average.
What I can say is that, for example, in dimension 7, which is like the first one where you see singularity, right? It's possible that the only area minimizing cones are the cone over S3 times S3 or the cone S2 times S4. Right? Those are the two that are quadratic and area minimizing in dimension 7. And it is not known if they are the only one, but there are no other examples. So if that, for example, was the case, if those two were the only one, which is possible, then this bound would definitely not be optimal in the sense that you could just, instead of log, you could just have the full power. My impression, looking at the examples that are in the literature and the type of results that are in the literature, this is though a very, very extreme conjecture in the sense that I have no idea if it's true or not, is that if you are looking at the top stratum, then it might actually be, so the first if you are in dimension n, you're looking at the stratum n minus 7, that might actually be always a power.
So this is like a meta conjecture about all the things.
This is a very strong conjecture. And then if you go down in the, because it becomes kind of a codimension 2 problem if you go down the stratum. And so there I bet you that there are examples where the convergence is at most logarithmic, where the regularity is at most logarithmic. Also, I should say, here I'm talking about, so there are two different questions, right? What is the regularity of the singular set and what is the convergence of the minimal surface to the cone? So what I think it should be C1 alpha is, for the top stratum, is the regularity of the singular set, not the convergence. That I think might still be logarithmic. So these are two different questions, right? Because the singular set might still be C1 alpha, even if the convergence is just logarithmic, even if the convergence of to the cone is logarithmic. But yeah, for example, in the obstacle problem is exactly like that, right? Because in the obstacle problem, as you know, in the paper of Joachim and Alessio, right, they prove that the top stratum is C2 and the convergence is C2, and then you have to go down to see the log. And isolated singularities, again, they are C1 alpha. So somehow the top and the bottom seem like they are more rigid, and everything in between seems like it should be worse. But
still there, it's not always clear the thing between is worse, right? I feel.
Well, in the obstacle problem, their example is logarithmic, right? They have an example of what is it in dimension 3, the one stratum, the decay is logarithmic.
Okay.
So, but yeah.
Thanks. Nice.
I have one more question. Is there any example of, let's say, a minimal hypersurface in a manifold of very high dimension that has a one-dimensional singularity that can't be perturbed away?
Not that I know of. That's
Okay.
a good question. Not that I know of. So I don't even think I know any result. But this is probably lack of reading on my part. But I'm not sure I know any result of where you can perturb away, say, a line of singularity.
Right. Okay.
In this context, again, in other contexts, that's possible. For example, again, in the obstacle problem, in the recent work of Alessio with Joachim and Xavi, they do it.
Mm-hmm.
But here, I don't think I've ever seen it done.
Okay.
This doesn't mean that there is nothing in the literature, though. Again, I admit, if you look carefully, maybe you find. I would find it strange because I think this would be a pretty, like, something substantial. I mean, it doesn't seem like an easy proof would work.
Oh.
So.
Okay.
I don't know. Yeah.
Thanks.
Thank you.
Well, any more questions for Luca before we wrap it up? If not, then thanks very much again, Luca.
Thank you, Connor. Thanks, everybody.
And
You can stop sharing this nonsense.
Luca, grazie del talk.
Oh, grazie a te. Ci vediamo.
it's good to see you,
Using
Francesco.
Italian, maybe it's not a great idea.
It's okay. They're still recording us, so we should be careful, maybe.
Okay. So,